To start. So good morning, everybody. Welcome to lesson 13 of CE 3372, Water Systems Design, Fall 2020. I'm getting feedback, so let me see what I can do about that, because that's annoying. Let's see, let me mutate everybody. There we go. Mute everybody. So you've all been mutated. I know that hurts having your DNA moved around like that, but the feedback is stopped. So what I'd like to do is, before I start the formal presentation, is address any questions that you may have regarding the homework and the exam, if you even started and looked at those. I had some emails this weekend that turns out my fine computer didn't bother to tell me they were a year old. So apparently I had an exam same time last year. And the emails were all saying, "Oh my God, I didn't get it done in time. I logged in and it didn't work," and I was like very confused until I looked and saw the dates on the emails, and it's like, well, that's spooky. So I thank IT department for not deleting things when you tell them to delete it. Well, when you issue delete command. But it brought up a point. Are there any questions? Okay, good. Well, if they're not, just a reminder, it's due on the 10th. So the emails this weekend, which weren't any of you guys, but there's over 70 of you in the two classes, and so I after a while everybody's name looks the same, and I'm sure for you after a while every professor on video starts to look and sound the same. Probably because you're asleep when we're talking. Uh, but that's beside the point. That's supposed to be a joke. Okay, well, so we'll get started with today's lesson, which is a review of open channel hydraulics. And so it's lesson 13, and hopefully the link is working. Oh, sweet, it is. And so this lesson is going to examine open conduit flow concepts for a particular type of steady flow called normal flow. The test is due on the 8th. 10/8. Yes, Matthew, that's correct. It's due 10/8. I think it's at midnight, but I wouldn't trust that, so I'd be sure I looked at it on the 7th. Examines open flow concepts for normal flow. So this, for students that have had the open channel flow class already, which you probably should not have, but there are some graduate students in this class taking this for leveling. This will largely be review for you. These are concepts that you should have had in fluid mechanics, but depending on the semester and the circumstances, it may have been quite short-changed on that. And that's not the end of the world. This is not that difficult to wrap your head around. And so we'll proceed at that. There's the lesson notes, which we'll go to in a second. I've posted 3 useful readings. The one is from the National Training Center by the United. I got these backwards. There's one, Basic Hydraulic Principles. That's from the National Training Center for the United States Geologic Survey. It's a copy of an open file report. You might actually be able to get the actual report by now, but at the time, this was the only copy I had. There's a second one, which is an entire chapter out of the hydraulics book that I had when I went to school. No, that's not right. The year is wrong. I went to school in the early 1980s, so I don't know. Maybe it's a different edition of the book I had when I went to school. So there's a chapter called Closed Conduits, and then the last one is out of Ralph Werb's and Wesley James' book, Water Resources Engineering on Urban Stormwater. Having a spelling trouble here. It's supposed to be management, not manglement. Oh, that's a pretty good funny misspelling. There are data links in the spreadsheets and scripts. There's some spreadsheets that implement some things, and when we get to that in the lesson, we will leave the browser and go take a look at those. So let's begin with the notes, and it should be lesson, a funny naming convention. They're supposed to be called, well, this looks right. Okay, it says fall 2020, so we'll go with it. And if it's on the computer, it must be right, right? That's an old joke from when I went to school. So back when I went to school, computers took entire buildings and they consumed staffs of operators, and all your printouts came on this paper that had horizontal bars on it, and there'd be like a 1-inch tall bar that was kind of a light green color, and then a 1-inch tall bar that was a white color, and then green again, and then white, and everything got printed in that, and it was called green bar. And we used to joke that, you know, it has to be right if it's on green bar. That later on became the joke that if it's on the internet, it's got to be true. So, buongiorno, everybody. So today's lesson is normal flow. So let's first review in our minds what's meant by the term open conduit. So an open conduit is a conduit whose upper boundary of flow is the liquid surface. Closed conduits, the upper boundary of flow is the physical conduit itself, and essentially the differences between pressurized and free surface flow. That's really what it's coming down to. So things that are open conduits that we're quite mentally familiar with are canals, streams, bayous, rivers, creeks, brooks, which run through the holler, and I think I said that right. I don't have my West Virginian dialect down so good right now, and if anybody's from that part of Appalachia, I didn't mean to insult you. That was supposed to be humor. And then things that we don't often associate as open conduits, but they are storm sewers and sanitary sewers, because they become special cases of open channels where there's a free surface. So if the sewage water gets to the top of the pipe that it's in and touches the top of the pipe, then that's no longer a free surface. That would be a pressurized system. Not very pressurized, one hopes. So a way to remember that is if you can visualize yourself floating in the flow, and somehow you can get your nose up to the surface and actually breathe. If there's a gas phase above you, then it's an open conduit. And don't try to visualize floating in a sanitary sewer, because there's nothing sanitary about that, and it's just a gross picture. The relevant hydraulic principles are the same whether it's a storm sewer, sanitary sewer, canal, stream, bayou, river, and so on. It's essentially a balance of frictional forces, gravitational forces trying to pull the water downhill, and pressure forces pushing the water about. And actually, I should be saying liquid, but we pretty much mean water. And then there's a couple of different flow regimes. And then what makes open channels different from pressurized flow system is that the flows can exist in a couple of different states. Whereas in a pressurized pipe, there's a pretty unique relationship between the head loss and the flow rate. That's not true in an open channel. There's a couple different flow regimes that can exist at a particular flow rate, and they change depending on what the slope of the channel is, its geometry, its friction, and a few other things. So for a given discharge, the flow at any cross section can be described by its depth. So how deep is the water, mama? 6 feet high and rising. The cross-sectional area, which in itself is a function of geometry. The elevation, which actually is what gives us topographic slope, and the mean section velocity as we defined last time or in prior meetings. The flow depth, depth area, depth perimeter, and depth top width relationships, they're all non-unique, which means there can be two different answers that still produce the same flow rate, depending on the flow regime. And the knowledge of whether the flow is subcritical, critical, or supercritical is important in determining which of the solutions that we will use in a particular application. Most of the flows we'll encounter in engineering in much of the world will be subcritical and critical, but supercriticals exist. They're common in environments with a fairly steep slope. So Albuquerque, New Mexico, the city itself is relatively gently sloped compared to the Sandia Mountains, but water coming off the Sandia Mountains achieves supercritical flow and sustains it actually almost till it gets to the Rio Grande. And so the hydraulic engineers there are dealing a lot with supercritical flow channels, which is different than where I used to live, which was Houston. Supercritical flow occurs in Houston, but not terribly often, and it doesn't sustain itself. We're dealing with subcritical and near critical flows there, and so we'll look into those more next meeting actually. So one category of flow is called steady uniform flow, or it's also called normal flow to distinguish it between normal flow and abnormal flow. Just kidding. Normal flow is flow in the channel where the flow depth does not vary as you're moving along the channel. And the key point in normal flow is that the slope of the water surface, which happens to be coincident with the hydraulic grade line, is the same as the slope of the bottom of the channel. So the flow has a constant depth regardless of where you look, at least in an idealized setting. So let's look at some drawings and some terminology of these situations. So here's a sketch of steady flow in a channel, and let's look at the important terms. So this line right here with these hash marks on it is representing the bottom of the channel. So the cursor is moving back and forth over the line with the hash marks, and it's showing here a triangle, which is indicating the change in elevation over change in distance, and it's labeled S sub 0 for bottom slope. Sometimes it's referred to as S naught. Same stuff that comes out of your nose when it's runny. That's S naught. And we have two sections here, cross section 1 and cross section 2. In this drawing, cross section 1 is upstream, cross section 2 is downstream of cross section 1, and that's the usual but not a required naming convention. So bottom water surface is this line right here, which has a little triangle with little wiggly things on it. And then there's this dashed line here, which we'll see what that is shortly. That's the energy grade line. And we've got an arrow indicating flow. And I drew this. This looks like my artwork. And I'm right-handed, so I tend to draw flows from left to right. So if this engineering gig doesn't work out for you all and you become a detective hunting down international terrorists, you can tell what handedness they are if they're hand drawing stuff by which way they indicate their flow arrows. I'd be very scared of a terrorist that can think like this, because they're going to be hard to beat. But if the engineering gig works out for you, you don't have to worry so much about it, because in some sense that's a form of job security as you get to rebuild stuff. A very grisly and morbid statement right there. So let's return to our drawing. Here's our bottom slope. And here is the water surface, which happens to be coincident with the hydraulic grade line. And this dashed line is the energy grade line. So let's look at a couple points at cross section 2. So at the water solid interface, where the water contacts the bottom of the channel, the height of that above some datum is the elevation. So I've labeled it in green here, And over at cross section 1, this point where the cursor is, let me move it a little bit so it gets captured by the video. That point where the cursor is the elevation of the bottom of cross section 1, Z subscript 1 in this case. Then we move up in the water column a distance which is labeled here as Y2, so that's the depth of the water at that point. And that depth is going to play the same role as pressure did in our earlier Bernoulli equation. And so the elevation plus this depth actually gives us the static head in the system. And then if we were to move up from the water surface to the energy grade line, which miraculously don't appear in real life, it's not like there's energy grade lines floating above anything. We can't see them yet. You need special goggles for that. This distance is proportional to the square of the velocity of the flow. So the hydraulic energy at a section is comprised of the elevation head, which is directly proportional to the elevation Z, the pressure head, which is directly proportional to the water depth Y, and the velocity head, V squared over 2G, usual meaning. So with those in mind, let's look at a little bit more sketching. So the hydraulic grade line is displayed on this chart in blue and labeled HGL for hydraulic grade line. And in open channel systems, the water surface elevation is coincident with a hydraulic grade line. They each meet the definition of hydraulic grade line. So that's in some sense, a nice thing about open channels is that you can see the hydraulic grade line. It's right there where the water is. Remember you're floating in this, putting your nose up in the air, trying to catch a breath. The energy grade line, as depicted here, is simply the hydraulic grade line location plus the velocity head to get up to the energy grade line. So if we look at the channel in the drawing, there's the bottom, and we see that the depth at section 1 is smaller than the depth at section 2. So this has a depth taper that's increasing in the direction of flow. The only way for that to be true if the channel is of constant geometry, say it's a rectangular channel, is that if the flow gets deeper, the area gets larger, so the velocity would decrease. And so we're showing that decrease as the energy grade line sloping downward. Now the forces that would make that happen are friction. So as the water's flowing downhill, friction's making it pile up a little bit on the downstream end. So we get a depth taper and we get a energy grade line with some slope. In this case, the slope is indicated here by this triangle. And this leg of the triangle is labeled S sub F. And S sub F is the slope of the energy grade line. And the more older term for S sub S is called the friction slope. So we have a friction slope, we have a bottom slope, we actually have a slope of the water surface elevation, but it doesn't have its own special name. So friction slope and bottom slope. And so the locus of the total hydraulic energy is called the energy grade line, plotted in red in this figure. And then lastly, I called the bottom slope the bottom grade line. It doesn't have its own special name, although in the NCH, the Federal Highway Administration and the TxDOT manuals call that the flow line. Got that right? Yeah, the flow line, or it might be called profile grade line, depending on the context. But we can call it bottom grade line. Here it's just painted in green, and so it represents the position of the bottom of the channel everywhere. And if we return to the energy grade line, if there were no changes in total energy in the system, the line would be a horizontal line, indicated here by this horizontal dashed red line. But here at section 2, we see the energy grade line is down here, and the distance from the horizontal line to where the energy grade line is called the head loss. And in this case, hydraulic head loss is somewhat different than the head loss that occurred during the French Revolution. So here's the French revolutionaries, and this aristocrat didn't really lose his head, kind of lost the body actually. But from the body's perspective, this is head loss. This kind of head loss and this kind are completely different things. And I hope the grisly historical picture keeps the idea of head loss from a hydraulic sense in your head. So it's gallows humor intended to remind us that we've cut the head off the body as we move downstream in our channel. And I want to go back to the green line and identify some other parts of the picture. So if we move from cross-section 1 to cross-section 2, this picture is depicting the distance between the two as some finite value delta x. And in this drawing, the delta just means change. It's not necessarily implying that it's an itty-bitty teeny-weeny change in x, although it could, but it just means the change in space. If we go to position 2 and examine what the elevation is at the bottom, it's at Z2, and at position 1, it's at elevation Z1, and so the difference between Z1 and Z2 is this distance right here, where the cursor is moving up and down. And that distance happens to coincide with the value of S sub 0 times delta x. So S naught delta x is the change in elevation. Similarly, in the energy grade line, we have a similar definition that says that the head loss is equal to S sub F delta x. So those two terms will play an important role coming up. And I think we've defined all the other terms. So uniform flow occurs when the two flow depths, y1 and y2, are equal. Based on the drawing, for that to be true, the friction slope, S sub f, would have to be the same as the bottom slope, S sub 0. And in fact, the equality S sub f equals S0 is the definition of uniform flow. And it's also called normal flow. I think uniform flow is probably better terminology, but it appears as normal flow quite commonly. A second flow regime that you would have had back in fluid mechanics is called gradually varied flow, and that's not normal flow. A gradually varied flow simply means that the change in flow depth moving upstream or downstream is gradual. And I have a comment here, not a waterfall. So gradually varied flow, the two flow depths, y1 and y2, are no longer equal, and that change occurs over relatively long distances. Hundreds of meters, if you will, is gradually varied flow. If that change occurs over a very short distance, like 1 meter, you get into waterfall regime there, that's called rapidly varied flow. And rapidly varied flow means the change in the flow depth occurs over a very short distance, on the order of meters. Examples of rapidly varied flows would be flow out of sluice gates. So those are, just imagine walls with a panel in it, and you lift the panel up and it makes a little opening at the bottom and the water goes squirting out there. It's a sluice gate. That's extremely rapidly varied flow because upstream in that sluice gate the water is not moving very fast, and in that part where it's squirting out it accelerates quite quickly. Another example are hydraulic jumps, which you would have had in your fluid mechanics laboratory, or flow through energy dissipators. Those are all examples of rapidly varied flow, which is outside the scope of this lesson and pretty much the class entirely. We'll talk a little bit about it, but you would have had that in fluid mechanics class. A classic fluid mechanics class is to calculate the approach and sequent depth in a hydraulic jump. And the trick there, which since you've all been through it, you would know, is that you don't want to use the energy equation because it's no longer conserved, but momentum is almost conserved, and you use that to do the analysis. And that's rapidly varied flow. So returning to our course, let's look at some open channel design concepts. So the reason we're designing these things is presumably to carry stormwater or wastewater, but for the time being, think of stormwater. And what we have to do as designers is we need to know what the system capacity is going to be. And once we have that, we can size certain components to make our drainage system do what we'd like it to do. So the first step would be to estimate the required system capacity, and that estimate's going to involve some hydrology analysis, or in the case of sanitary sewers, the number of anticipated service connections. Our second step would be to use a uniform flow assumption. So we'll assume a uniform flow prevails to size the conduits with adequate freeboard based on our design documents, select slopes, and attempt to achieve design velocities. You could stop at step 2 and hope that the design is going to work, but the prudent engineer would do some remaining steps. You would evaluate your design using a hydraulic model, and it would be especially important if you're working in regimes where there's going to be some kind of backwater. If it turns out the hydraulic model is satisfactory after step 2, then you could conclude that the design is likely to be hydraulically adequate, and if that's not the case, you want to adjust the design to try to achieve hydraulic adequacy. And then you would want to check that the other non-negotiable constraints are satisfied: alignments, right-of-ways, setback distances from other systems, and so forth. Have you met your aesthetic requirements? Have you done the this is not going to move. Have you done the necessary archaeological survey and so forth? And step 5 would be iterating between 3 and 4 until you have some workable alternatives. Workable meaning they're hydraulically acceptable, and there's something that you could design and build for your client. And then you make cost estimates, present to the client, and let them make a decision. So the conduits are the pipes, and to size them, we have to know some things. Once we select a pipe material, and we select a pipe slope that we're going to put the pipe in its trench at a particular slope, then we need to determine the depth area, depth perimeter, and depth top width relationships in a cross section. And these are used to evaluate the hydraulic adequacy of whatever we design. So let's look at the first one, the effects of geometry. So regardless of the type of cross-section, the depth geometry of functional relationships are all based on the same common theme. They're based on us coming up with some way of explaining the depth versus flow area, depth versus perimeter, and depth versus top width, because these three relationships appear in the head loss equation, which is used in open channel, which is usually Manning's equation. So let's look at the first one. So this figure is a diagram of some arbitrary cross-section. It's supposed to be arbitrary. It looks pretty darn rectangular to me, but let's set that aside for a moment. And there's some letters of the alphabet on it, and let's explain what they are. So this curve, where the cursor is following with these shade marks, is supposed to represent a cross-section of some open channel. Actually, I think in nature you wouldn't find one that looks like that. It looks a little bit too humanly engineered. It was certainly humanly drawn. At the lowest point in the channel is a location which, if we join them up from station to station and use that to draw the channel from a bird's eye point of view, or plan view, like on a map looking down. That collection of points is called the Fallweg. It's a German word. It means valleyway. From that lowest point up to the water, we measure the depth. And so from the Fallweg to the water surface, that's called the flow depth, and that's indicated by the letter Y in this drawing. If when we get up to the surface, we visualize a little teensy extra layer of water there that's dy units thick. In this case, dy is a small number. And at the water solid interface, we can define the top width, which is indicated by the letter T. The added area that would occur if we added that additional layer of water that's dy units thick is dA. And we will be able to relate dA to T and Y on the next figure. In doing that, we find out that dA equals T times dy. And here in the diagram, it's been written as T of Y to indicate that the top width is functionally related to the flow depth. As these cross sections get complicated and have little hills in them, and you get streams splitting and rejoining, the same principles are still true. They're just a little harder to write in a nice, concise, functional form. So if we were to integrate dA, the differential area, from the bottom all the way up to some total depth, we could come up with this integral. Top width times tau, which is the variable of integration, d tau. If we integrate it from 0 up to y, that gives us area as a function of depth. Now the integral form is nice for presentations like this, but nobody actually uses it. Instead, what we would do is we would numerically approximate that integral to accommodate strangely shaped cross sections. But at least in terms of some sort of calculus explanation, we have it. The area is simply the integral of the top width with respect to depth. The next term of interest is something called the wetted perimeter. And in this case, the wetted perimeter is indicated by this red line. And that red line locates all the points of contact between the water and the container. And so as y gets smaller, we would expect this red line to get shorter. In fact, if y goes all the way down to 0, the red line degenerates to a point which has no length. And as y gets bigger, we get more and more of the side contained. And see, did wetted perimeter, top width, and area. So the purpose of the wetted perimeter is to define a derivative hydraulic variable called the hydraulic radius. So let's look at these ideas in a rectangular conduit. Rectangular conduits are certainly the simplest to consider, and these are legitimate because a lot of engineered conduits are indeed rectangular. Box culverts that have a free surface are an example of such a geometry, and in many urban drainage systems we have need or opportunity in some locations to actually have to build rectangular conduits. It's not the best cross-sectional choice, but it can be made to work. If it's a rectangular conduit, it's going to have to be concrete lined. It's impossible to make a soil-lined rectangular channel stay stable. The angle of repose is not 90 degrees, and so eventually the soil would fall in. So here's our rectangular conduit. The usual terminology is the bottom width of the conduit is the letter B. The top width, which is a property of the water, not necessarily the conduit itself, is shown here. And Y is the flow depth above the Fallweg bottom, which on a rectangular conduit that's flat like this one is going to be anywhere along the bottom. If we were to calculate the area of the blue rectangle that's shown there on the display, we would see that the area is equal to T times the quantity y, the top width times the depth, but it turns out the top width is a constant. It's the constant b, so we would write the area as b times y. So area in a rectangle is bi. The top width is the constant b, and then the wetted perimeter is the length of the water solid contact. So we have b units of length right here along the bottom, and we have 1 unit of y on this side and 1 unit of y on that side. And when we add all those up together, we have that the wetted perimeter is equal to the sum of the bottom width and twice the depth. So those hydraulic variables are fairly easy to compute and understand. The ratio of the area to the wetted perimeter is a derived hydraulic metric called the hydraulic radius. And it's important because it's used in many of our head loss equations. So in the case of rectangular geometry, the hydraulic radius is the area divided by the wetted perimeter. We've just computed the area as b times y, and the wetted perimeter is b plus 2y. And we can examine the case where the channel is really wide, so b is really big compared to y. If that's the case, if b is really big compared to y, the hydraulic radius pretty much degenerates to just the flow depth, because b plus 2y, when b is big, is essentially b. So you have b times y over b, the b's cancel, all that's left is the y. So as a way to keep in mind, if you've selected a hydraulic radius correctly, its numerical value shouldn't ever get much bigger than the flow depth, and probably is kind of close to flow depth. Not close enough that you want to write it down and get sued because your project failed, but just as a rule of thumb, it shouldn't vary hugely from whatever the flow depth. So now let's repeat that thinking for a trapezoidal channel. And trapezoidal channel is actually a reasonably common, it's a very useful geometry. Because the triangular channel and rectangular channel happen to be special cases of this channel, and natural channels can often be well approximated using trapezoidal channels. So natural channels are all wiggly and rough, but they take on a pseudo-trapezoidal shape, and if you're in a hurry or doing just an initial conceptual analysis, then it's a good approximation for natural channels. And the geometry is pretty common in drainage engineering for engineered channels. If you're from the Houston area, the bayous that you've driven by, that the flood control district operates, are largely trapezoidal channels. They have a rectangular pilot channel down in the middle, but they're trapezoidal channels. And this term, the side slope on bayou channels, is pretty steep. It's 2 to 1. But other trapezoidal channels you're familiar with will have 6 to 1 side slope. And the 6 is not a hydraulic choice. That happens to be the side slope that the FHWA has determined is something called traffic safe. So what traffic safe means is you can take your pickup truck at 85 miles an hour and drive into a 6 to 1 side slope and live through the resulting accident. And you know, in a good world, you actually might even get to the other side of it and the vehicle still be operable. So let's examine the hydraulics of the trapezoidal channel. So the area of the trapezoid is drawn up here is y times the quantity b plus my. And in this particular set of equations, I've implicitly assumed that the side slope on each side is the same. They don't have to be. If that's not the case, you would have to analyze it as two different triangles plus the center part. The top width in this case is b plus 2 times my, where m is the run for each rise along the side slope. The weighted perimeter is b plus 2y times the square root of 1 plus m squared. So what's going on there is the length of that side of this triangle is determined by Pythagorean theorem. And since they're identical triangles, there's two of them. And the length of that triangle is obtained from the slope. And then we add that to the bottom width b to get the total weighted perimeter. And then the hydraulic radius is the ratio of those two. And with the exception of the rectangular channel, there's not much to be gained by trying to simplify this further from a mathematics sense. Generally, we just calculate that value, numerically calculate that value, and then make the requisite division. So we have an online tool that does allow us to do this with different side slopes, and we will go out and visit that because I hope I have it working. And but let's see if we can do that in a separate toolkit. I want open channel hydraulics, trapezoidal channel, and it's broke. Of course it's broke. Go to the right toolbox, it should work better. So go to the Atomic Kitty box, and see, these don't have dates on them, so I don't think they've been checked. Well, here goes nothing. Okay, so here's our trapezoidal channel. And so to calculate the hydraulic conditions, what it's going to return is it will compute area, it'll compute top width, weighted perimeter, hydraulic radius, and then something called the hydraulic depth, which we're not going to use much in this class. Let's look at the example that was being shown. If this Zoom thing will get out of my way. Let's put it down here so it can be in the way down there instead. So let's look at a channel that has a bottom width of 5 feet. Both side slopes are 6 to 1, and the flow depth is 3 feet. So the bottom width was 5 feet. The both side slopes are 6 to 1. And the flow depth was 3 feet. And if we run this, it should do all the arithmetic for us, and fails. And let's see why that happened. It keeps going to the wrong. That's frustrating. Well, it doesn't do anything right now. And I don't want to. Well, let me see if I can fix this in a hurry. I know what's wrong. I don't think I can fix it fast enough to be useful for this class. So I will repair that after the lesson is over. It's going out. It's trying to go to the wrong server. I'll show you what it's trying to do. So when I click on this, it's supposed to go to Atomic Kitty DDNS CGI bin and then find the Python script that evaluates it, but instead it's going to a machine called Theodore MacBook Pro, which doesn't exist anymore. And if I try to simply insert what I think is the correct URL, it does not work. So I'll have to repair that. So had it worked correctly, it would have returned top width of 41 feet, weighted perimeter 26 feet, flow area of 69, hydraulic radius, and hydraulic depth. To do a rectangular conduit, we turn the side slopes to 0, and then it will simply operate on the bottom width and the depths. And to do a triangular conduit, it's a triangle, we run the value of b to 0, and then you have a triangle that's based on the side slope. So it has the functionality to handle 3 of the main geometries. The other geometry of interest is the mighty circle. And so in the circular geometry, let's look at the definitional sketch. This is supposed to be a circle, although I have to confess it looks like an ellipse to me also. And this would be a case where you have a pipe, but it has a free surface. So the flow depth is measured from the bottom of the pipe up to wherever the water line is. And it creates this blue shaded sector in this drawing. And the distance from contact to contact at the water-solid interface at the free surface is the top width. Because it's a circle, we actually know some other properties. If we know its diameter, we also know the distance from the centroid to that contact point is radius. And likewise, we know the distance from the centroid to the contact point on the opposite side. And so with that information, we can determine what the sweep angle is. And depending on the literature source you use, some authors present it as a half angle, as I've done so here, and some authors present it as the angle from radius to radius. The end result is the same, but if you're building these yourself or doing your own analysis to be sure that you trust the geometry in somebody else's table, be careful that you have selected whichever angle you want to analyze and you stick with that, at least throughout your development of governing equations. So using this half angle approach, the angle alpha of this portion from the vertical bisector to the radius is the arc cosine of 1 minus 2y divided by the diameter. And you could verify that yourself by drawing the necessary triangles. Once we know what that angle alpha is, we can compute the area of the circular sector, the blue circular sector here, as d squared over 4 multiplied by the quantity alpha minus the product sine alpha cosine alpha. And in these cases, alpha has to be expressed in radians. If you do this in degrees, it will confuse the heck out of the calculator and be wrong. Once we have the area, the top width is easy to obtain. The top width as a function of depth is simply the diameter times the sine of alpha. And the wetted perimeter as a function of depth is simply the diameter times alpha. The hydraulic radius is the ratio of area to wetted perimeter, and only a fool would attempt to reduce this further. I can safely say that because at one time I attempted to reduce this further and deduced after a while that I was a fool, and if it wasn't in a book somewhere, that means nobody else was able to solve it either. So likewise, we have an online tool that for grids I'll go to, but we already know it probably doesn't work. In this case, you would enter a diameter. You can enter a depth, hit submit, and you'll get the same error message. I will get that fixed. But if we'd entered a 6 and a 5, it would have computed the top width, the angle alpha, the wetted perimeter, the flow area, hydraulic radius, and hydraulic depth. Oftentimes, we're dealing with a geometry that we use over and over again. And if that's the case, it's often useful to create your own definition sketch and your own equations and save that in a binder somewhere and call it your own depth area diagram. Not a discgram. I think that's supposed to be a diagram. Looks like S is next to A. Or maybe you can call it a discgram. Some other geometries are common, and you would go to the trouble to do this if you're working on a project and you have to do hydraulics over and over again, and you're using common geometry. So, for example, you're using box culverts is easy enough to do. You can do that as a one of every time. Circles the same way, but sometimes it might be easier just to build a chart that you can look at really quickly. Elliptical pipes, you would have to build a chart to look at or do the arithmetic every single time. And there's a few other geometries that it would be useful to produce a depth area diagram. Another alternative is to build calculators. By calculators, I don't mean that you're soldering electrical components together to do the calculations, although you could do that, but that would be a bit overkill for a hydraulic calculation. But I mean scripting a tool that you use over and over again, and once you trust it, it saves you from having to re-examine how to do it. I have something called 9010T sheet, which are the computation sheets I built a while ago to help me do these if I'm using a hand calculator. None of the arithmetic is hard, but anything you can do operationally to relieve you of the need to go look up how to do stuff and create it from scratch again is beneficial in terms of time saving. And the last one is to use a dimensionless chart, and we'll look at some examples of that. So the first approach is just to build a calculator that does circular conduits for Manning's equation and never look back, never even think about it. So here's Manning's equation in US customary units. And we saw it earlier in the class as a head loss equation. Here it's written as a flow equation. Same equation, rearranged. And it says that Q is equal to 1.49 over Manning's N, the roughness coefficient, times the cross-sectional area of flow, times the hydraulic radius raised to the 2/3 power, times some slope, supposed to be the energy slope, to the 1/2 power. Oftentimes we use the bottom slope, and in doing that we are implicitly assuming that it's normal flow. And I would say a drainage engineer in the US should memorize that. And if you were to look at the readings in Chin, you would find out that these are adaptations of that in US customary units. And we could go build a calculator in Excel. It might look something like this, and we'll go take a look at this actual one. And if we do that, it gives us a tool that we could input data as needed and calculate values as needed, and it's not all that hard. Or we could decide I'm not always going to have Excel, but I'll always have a phone, and I can go ahead and build a web application and then just access it via my telephone. So here's another example of one. And we'll go look at the interface, knowing full well it's not going to work. Slope area discharge. And again, you put Manning's N, flow area, wetted perimeter, slope, and hit submit. And so a fair question is, why are we entering area and wetted perimeter? The reason we're doing that is this handles any geometry, and we use one of our geometry tools to handle the other case. And there's also one that's done in Oh, this one might work. That looks like a JavaScript to me. I'm just putting numbers in here just to see if it will run. Ah, cool. So this one ran because that was a JavaScript instance. I wonder if the other one is JavaScript. Doesn't look like. So part of what I'm doing is figuring out what homework I'm going to have to do. Oh, that one worked good. Okay, cool. I will explain how to use those. Let's go back here. So let's suppose we want to apply the slope area method to something that has a Manning's N of 0.013, cross-sectional flow area of 69 square feet, weighted perimeter of 26.6 square feet, and a dimensionless slope of 5 parts in 1,000. So literally I have to go look at it again because my memory stinks. 0.013, flow area, 69, weighted perimeter I forget, but this was 5 parts in 1,000. Weighted perimeter was 26.63, which we obtained from earlier online tools. Hit the submit. Ta-da! And it tells us that the discharge is 1,054 cubic feet per second, and hydraulic radius is 2.59 feet. Section velocity is 15 feet per second. So from a design standpoint, if we were designing a channel, that section velocity would be too high. It'd be difficult to design a stable channel of that, and we would look at some geometric changes to try to reduce the velocity. So that's an example that worked of the online tool. And then if neither of those are available to you, we can always just fill out the ID10T sheet as an income tax return form. And so let's go take a look at what that is. Well, it's in data. So I have one for U.S. customary and SI, and literally made this, looks like the last update was 2017, probably fixed some spelling errors at that time. So this is when nothing's available. You just put in Manning's N depth, and it tells you what to do. So copy the value from line 1, put it here, line 8, put it here, line 10, put it here, line 4, put it here, compute the square root, compute the 2/3 power, multiply, blah, 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 and you get your answer in cubic feet per second. So that's really an old-fashioned interface. The value of doing it on something like that is once you write it down, you have documented your work. So let's return to the presentation. So those sheets are intended if you have just a hand calculator, although I've used earlier versions of that I made back when I was in college. That all you needed was a table of logarithms and a pencil and a flashlight if you want to do it at night, and you could do those calculations with just those tools. So here's an example of the sheets in U.S. customary and SI. And now we get to the dimensionless diagrams, which I think are very useful. And we will go over those a little bit. This is admittedly old school compared to what you're all used to, and I'm making an assumption here that you're in your early 20s and you kind of grew up with computers. So you didn't have to use graphical tools to solve problems. But in the olden days, when dinosaurs roamed the earth, this was all we had. And so using the same principles as a calculator, we actually can plot solutions to Manning's equation in something called a dimensionless diagram. And then using the plot and actual dimensions of the problem, obtain dimensional results. So here is an example of the calculations that would go into making a dimensionless diagram. So this is done in a computer spreadsheet. This has to be done first, but you only have to do it once. So this could be done by hand on paper. We have Manning's N, we have diameter, we have a slope, and we postulate different flow depths in the object. We produce a ratio of flow depth to diameter. So this column right here is one column that we're going to use for making our diagram. Then we have some intermediate computations where we calculate that angle alpha, the flow area, the weighted perimeter at these different depths, and the hydraulic radius. Then from that we compute discharge in actual units, and then we divide that computed discharge by the discharge when the pipe is full, and there should be by pipe full means that we compute the flow depth down here, this last line. Pipe is full, and we have the discharge ratio to full. So we compute discharge divide by full, and we declare that that 79 becomes a 1, and that rescales all these. And we get a plot that looks like this. And so on this plot, if we know a flow depth ratio, we can recover a discharge ratio. Now the calculation of full discharge is easy. So that's just Manning's equation applied in this fashion. And here's how we would use a chart like this. First, we would calculate the full pipe discharge. Manning's formula, area, hydraulic radius. If the pipe is full, these terms are pretty straightforward to determine. Slope to the 1/2 power. Usually we use pipe slope, so we'll assume it's normal flow. Then we determine the flow depth ratio of interest. Let's suppose we're interested in what's the flow at 3/4 full. So the ratio is 0.75. We go to our chart, we find the 0.75, which is somewhere in here. We read up here and we recover the ratio, the 0.75 flow depth, and we recover the flow ratio. It looks like it's somewhere bigger than 0.9. It looks like 0.911. And then multiply the discharge fraction that we just looked up from the chart by the full depth to obtain what we would call the Q75. And we find out in our case that the 75% full pipe would flow at 0.911 multiplied by the full flow rate. And it gives us a very quick way to evaluate the amount of discharge carried at different depths. There's a similar chart in the NCEES supplied reference, which is the FE exam reference, and what we just showed in the Excel table was the formula that computes the discharge following this shaded line. So it's a shaded line where the friction factor and Manning's N stay constant with depth. And the value of these charts actually comes in when we're using it the other direction, which is suppose we want to determine a design diameter at a required fill depth and supplied discharge. And so that would be common because in both storm sewer and sanitary sewer design, oftentimes their guidance document says, sewer shall be designed to carry flow at half full at the design discharge, in which case we need to know what the diameter has to be to carry a particular discharge at 1/2 full. And so we can work these tools backwards. So we would go to the 50th percentile flow line. In this case, it's showing that we would be half full and we can solve for diameter. In sanitary sewers, usually that criteria is somewhere around 0.75, 3/4 full, or even 0.8, in which case the chart becomes more important. So at 0.8, we're at 0.65 full and use that to select a diameter. There are some other dimensionless charts that are available. One example is shown here. This is out of HEC 22, which is a Federal Highway Administration manual. I believe it's called Urban Drainage Design, but I may have the title wrong. And in it, there's a lot of charts. I just picked the trapezoidal channel chart. At the time, this would have been considered easier. So we have a slope, bottom width, and a design discharge multiplied by Manning's N. So this is the QN term. So the analyst would specify the channel width, the side slope, the longitudinal slope, material properties, and the discharge. We would locate the value of bottom slope on the first vertical scale, so this scale here, and then we would compute the product discharge times Manning's N, and then locate that value on this second scale. We would join the two values by a straight line. So we have some straight line, and there's this line called a turning line, and so we would indicate where the intersection occurs is right there. Then we would locate the value of bottom width on this scale, and we would join the turning line intersection to bottom width with a straight line, and it hits this portion of the chart, which is the ratio of depth to bottom width for different side slopes. So side slope 0, 2, 4, 8, and so on. And then once we've hit the edge of this, we move horizontally to our side slope of interest, and that returns in these curves the d over b value. And then we multiply that by the known bottom width, and it will tell us what the flow depth has to be. So in the 1970s, this was a useful tool. Nowadays, you probably would handle it computationally, but the nice thing about this is it documents your computational effort, and it's a way to check your work. So let's go look at some of these spreadsheet examples. So this first one, I'm pretty sure is going to be the table that was used to produce that depth discharge plot. Indeed it was, and if, if we want to, we can always change the pipe diameter. Make it a 5 diameter pipe. Notice how the plot didn't change a bit. And that's because dimensionless charts, by definition, stay dimensionless. They shouldn't change. We can change Manning's N, something smaller like that. Chart doesn't change. Change the bottom slope. Chart doesn't change. But what did change is the computed discharge, computed velocity, and the flow depth to discharge ratio. So I don't want to save that. So that's one tool that's available to you to use in this class and other classes. So here is a calculator to compute circular pipe flows in SI units. So it tells you to enter the depth, diameter, the longitudinal slope, Manning's N, It'll return the intermediate computations. It'll calculate discharge and velocity for you. And looks like B5. It'll actually produce the depth diameter ratio for you. So let's try a different value, Manning's N. Let's use a 3-meter diameter pipe, which is kind of big, and we'll go 2 meters deep in it on a longitudinal slope, 5 parts in 1,000, and that will carry 24 cubic meters per second, which is a lot of water, at 4 meters per second, and the depth to diameter ratio is 0.67. So these are pretty easy to build yourself, but it's nice to have one already done because then you don't have to think about it. And we have same thing in US customary. Not quite as pretty, so I guess we could make that pretty. Green is good for input, intermediate, neutral, output. Let's go yellow. So you can give yourself visual reminders. Let's go with a 6-foot diameter pipe, and we'll go 5 feet deep in it. And if we do that, a 6-foot pipe with 5 feet will carry 430 CFS at 17 feet per second, which is a bit much. And suppose it's on a shallow slope like in Houston, and our goal is to keep our flow rate less than 10 cubic feet per second. So the best thing to do is go ahead and disappear the spreadsheet, and everything goes away. We can try making the diameter bigger. We're trying to get 304, so we could use our goal seek tool, which should be tools, goal seek. I want to make that equal to 304, my design flow. I'm going to do that by changing the depth. Press the okie dokie button. And 7-foot diameter pipe at 4 feet deep still produces 12 cubic feet per second. And so we would have to explore some other ways of accomplishing that. Let's see what happens if I do 9. And so on. So it's a computational tool that can help us make some design changes to try to control the velocity. Looks like if we jack with the slope a bit, we can maybe get it. We're close. So a 9-foot diameter pipe, 6 feet flow depth, gives us our 304 cubic feet per second at 6 feet a second. So we can adjust slopes and diameters in an effort to control velocity. And that's a activity that we have to do during design. All right. These other ones, we'll just take a look at one of them. I think these actually replicate the tab. Yeah, these are the same thing. It's just another way of producing tables. That concludes the examples. I showed you the homemade calculation sheets, and these are just done for circles, but you could make those for any geometry that you're likely to encounter a lot. And that may seem kind of stupid to you, but sometimes having that handy is really useful. And I will conclude the lesson pretty quickly here, but let's go look at the readings so I can give you some guidance on what to look at if you choose to look at them. So first I'm going to the open file report, and it has the basic principles of flow and open channels. And I'll just scroll down arbitrarily. And goes through all the theory that I just summarized. So this is a good reference tool, and if you were to work through each of the chapters in it, you'd have a pretty good understanding of open channel flow, steady behavior. The next one is an entire chapter out of an old book. You can tell it's old by the sepia-looking page color, and it too goes through most of the definitional work that we just summarized in the presentation, and gets to Manning's equation quite quickly. I would suggest that this is a good reading, and we've seen this picture before because we just made it ourselves. Then it goes into trapezoidal channels and so forth. So I would recommend at least skimming through that chapter 4. And then urban stormwater management is much more of a conventional textbook approach. Talks about stormwater collection system. Oh, it's scanned in backward order. Classic Dr. Cleveland scanning. So you'll have to do some sorting of the pages to read through it in a meaningful order. But it's going through the hydraulics of stormwater. So if you're wanting to do some reading, I would suggest going to Open Channel Flow by Robertson, Cassidy, and Chowdhury. It's only 70 pages of reading, and it's got a lot of pictures, so it wouldn't be that hard to read through it. And then I would recommend that you take a look at this basic principles of open channel flow, familiarize yourself enough with it so you know your way around the document if you have to refer to it in the future. And then if you feel up to it after those 2 readings, maybe work your way through urban stormwater management. If you were to download the PDF, I think you could reorder it so that it presents in sequential order. At least the page numbers are included. And with that, I will try to get back to the chat. Check on everybody, and I will end the call now. If you have questions that you want to ask in front of everyone, now's a good time to unmute yourself and ask it as I am shutting down the phone call. Okay, how do I get back to control? Share screen. There we go. Stop sharing. All right. Well, the only question that was there was one that was posed earlier. Is the test due on the 8th? And the answer is yes. And okay. Yes, negative pressures on EPA net is a problem because I'm pretty sure none of the problems should have negative pressures. The usual solution to that is to check that you've entered the node elevations on every node correctly and that your supply reservoir has enough operating head to produce positive pressures. And it's okay to go to the supply reservoir and put some large value of head in it just to alleviate the negative pressures. If that does it, then it's usually an elevation conceptualization error. Let's see if I have EPA net on this machine. I'll go ahead and make up a problem real fast that will have the negative pressure error. See if I have anything I can open. I'll have to build one real fast. Bear with me. That should be a good enough network. Let me go ahead and put a demand here. There we go. So it says negative pressures, and if we go look at each of the nodes, it doesn't report pressures when we get negative pressures. The reason being, if we were to look at the nodes, let me go ahead and render the heads and view options. So it doesn't do a solution, but if I go to this reservoir and give it enough head to actually push water through, we'll see what happens there. And now I have positive values of head in the system. And if I
Sir?
Yes?
Can you share your screen, please?
Oh, I wish you had done that to me sooner. Sure.
Okay, thank you.
Okay, so I built this network. Let me go ahead and get the error back. Each of these nodes has elevation 0. And let me just go ahead and put some demand in them. Okay, so that's pretty easy to fix. Let's say these are supposed to have elevation of 100. We use group editing. I will put the elevation with 100. Choose the okie dokie. And now everything has elevation of 100. We can check that with this browser. And it's reporting 100 elevation. Here's my reservoir. Let's say I forgot to put a correct value for the reservoir. So right now it's showing up as reservoir elevation 0. Let's switch everything to head. So the reservoir has a head of 1. Attempt to run it, and I get this warning, negative pressures. So what that's telling me is I don't have enough head to drive water through the system. If I change it to 100, I think I'll still get the error because I still don't have enough head yet. Still get the error. But if I change it to like 100, 102, 120, Now the run was successful because I actually have enough head in the system, and I don't have very much head loss in these pipes. That's because they're not long enough. Let's go ahead and fix that real quick, make this a little bit more realistic. Oh, it doesn't, oh, let's see, conduit. Oh, won't let me, won't let me replace the length. Ooh, I just broke something. It's bizarre. So these are 1,000-foot long pipes, 12-inch diameters. It's using the Hazen-Williams model. And now I have a successful run, but when I switch my rendering to pressure, I still have really low pressures at the nodes. And if my goal is to hit 35 psi, looks like I need to add at least another 22 psi to it. So let's see what happens if we run at 144. Not quite yet. Another 15. And the reason it doesn't scale linearly is it's nonlinear behavior. So 15 would be 40, 50, 60. Let's just go over, no, not 1175, 175. Run it. Now I'm getting close. A little bit bigger, I could get my 35 psi. So the zero pressures means you've conceptualized either a supply node wrong or the elevations of one of the nodes is really wrong. So as an example, let's put node 8, 800 feet in the air. So I made an elevation mistake. I run it, and it can't get water to that node. It doesn't know what to do, and it issues the error message. So to answer your question, yes, you want to fix your solution until you don't get negative pressures. The two problems can both be done with that. You can do it, the first one's easy. You do pretty much just what I did here. Go ahead and attach a reservoir to node 1, jack with the reservoir until you get the pressure at node 1 to, I think that's at 100. I get the head at node 1 to 100 feet and get the other nodes and you're done. The second one where you do the somewhere USA, your initial supply is 135 psi. If it turns out that that's not enough, go ahead and artificially jack up the pressure to get stuff to flow through the system so that you can verify that your other elevations are correct. And then we'll go back in subsequent work to figure out how to add a booster pump into that. So Adrian, does that confuse you even more or give you some guidance? So I'll go give you more guidance. That's good to go. Okay, so thank you very much for asking, and I am going to stop sharing, and I'm going to end the phone call. If you all have other questions, you can email me, and I will try to address those. So what's coming up next is on the 8th, which is Wednesday. The exam 1 is due. So look at it either tonight or tomorrow. Don't wait till Wednesday to do it, because then you're trusting the servers to work. So with that, have a great afternoon. Sorry I went over, and I'll see you on Thursday. Bye, everybody.